What's up, everyone? In this lesson, we're going to be talking about inscribed angles. So, an inscribed angle is an angle that has its vertex as a point on the circle. Now, the other angle that we've learned about with circles so far is a central angle. And the main difference between an inscribed angle and a central angle is that a central angle's vertex is the center of the circle. So, we'll see an example of both of them in a diagram on the next slide, but there's an example of an inscribed angle in this diagram here. Now the vertex of the angle has to be a point on the circle, and then we draw parts of the angle out again until we're hitting the circle again. So there are infinitely many inscribed angles that can be in a diagram. I can choose this point on the circle here and extend these segments out to the other edge, right? I can pick this point on the circle here, and as long as the point on the circle is the vertex of the angle, then you are good to go. That's an inscribed angle. Now, the inscribed angle theorem is the main thing that this lesson is going to be a part of. So, one of the parts of the inscribed angle theorem says that an inscribed angle measures half of the value of its associated central angle / arc measure. Now, for this, the central angle and the inscribed angle must be intercepting the same arc in order to use this property. So this is the diagram that I was talking about before, where in green, right there, in green, we have our central angle, that the vertex is the center of our circle, right? So what this theorem is saying is that there's going to be an inscribed angle, which we see in red, that intercepts the same exact arc as our central angle. Now, to intercept the arc means if you take a look, and we can do this in like this brownish color. If you take a look at the central angle, right, and you take a look at the points that the central angle is ending, the intercepted arc connects those 2 points of the angle, right? So if we're looking at the intercepted arc of the central angle, it's this brown region here. But that's also the same region if you follow the sides of the inscribed angle here. That's also touching the endpoints of that same brown region that we've highlighted for the central angle. So now this is just some prior knowledge that we might need to use for this lesson. But again, an inscribed angle is half the value of its central angle, but also half the value of whatever arc it's intercepting. Where this GeoGebra is going to help us get a visual of taking a look at when angles are intercepting the same arc. So this is kind of the standard example that we see, and this is the standard example that we showed in the slideshow, but this can look kind of weird. So again, when we're looking at the arc that we're intercepting, you want to take a look at where your angle is meeting the circle and just highlight that region, right? So if we're taking a look at our central angle here, and this is where highlighters can really help you, if we're taking a look at our central angle that we've highlighted in red, if we highlight our inscribed angle in a different color, and we highlight the arc that it's touching, we can see that they're intercepting the same exact arc, right? So if your central angle and your inscribed angle are intercepting the same arc, then you're allowed to use that property. So, now sometimes this might be really nice and easy to see, like in an example here, but if I drag this point D around, notice that when I move D, I'm not changing the arc that I'm intercepting, right? If I move D here, and I highlight the intercepted portion of my inscribed angle, that's staying the same exact as the arc of my central angle, right? So in an example that looks like this, we'd be allowed to use that property as well. And again, no matter where I move this point D, I'm still intercepting the same arc. And you can kind of take a look at the angle measurements that are in here, right? So if this angle of my central angle is 58.4, this angle is staying at half of that value at 29.2, and you can see that that's not going to change, which means that no matter where I move this point D, I'm still intercepting the same arc. And you guys, this is just to kind of get a visual of kind of seeing how weird these diagrams can look, right? And again, the first thing you should ask yourself is my central angle and my inscribed angle intercepting the same arc? And for this, you can use highlighter. Right? So the first thing you want to test is to see, hey, is my central angle and inscribed angle, are they intercepting the same arcs? And if they are, then you are good to go. So for the second example here, our central angle is intercepting this portion of the circle. And if you guys have highlighters, you should be using 2 different colors to do this. So our central angle is inscribing that red region. our inscribed angle is also highlighting that same exact region, right? So in this case, we would be allowed to use that theorem. Now in this example here, our central angle is kind of intercepting the circle between these 2 points right here. And then if we take our second color and highlight our inscribed angle, we can highlight again those 2 points, and we can see that they are intercepting the same arc, so we'd be allowed to use that theorem. And then last but not least, in this example, this one's a little bit weirder, but our central angle is this whole entire 180 right here. It's that diameter. So if we take a look at our central angle, the piece of the circle that we're intercepting, or the arc that we're intercepting, is this region between those 2 points right there. And if we highlight our inscribed angle, we can see it's also highlighting the same exact region of the circle, so we again would be allowed to use that theorem. So in this case, our central angle, we're cutting the circle in half, so that's a diameter. So in this case, our inscribed angle is going to be 90 degrees. So again, the idea here is figure out if your inscribed angle and your central angle are intercepting the same arc, and you can use highlighters for this, because this will help you fill in some information. Now, does the central angle need to be there? No, because the theorem says that an inscribed angle measures half the value of its central angle or the arc measure, right? So in some examples, you might have that the arc measure is 60 degrees, and you're going to be expected to make this connection that if our central angle was there, it would also measure 60 degrees, right? Which means that our inscribed angle would measure 30. But your central angle does not need to be there, because this theorem talks about the arc measure, right? So if your arc measures 60, then your inscribed angle is going to be 30, and this logic can also go the other way. Let's say you're given an inscribed angle of 45 degrees. We can apply this theorem going the opposite way to say that, hey, this arc measure is going to be 90. Now, this is a non-example, so in all the examples we've done before, our angles were intercepting the same arc of the circle, but in this case, if we take a look at our central angle, we can see that we're intercepting the circle between points S and T, so this arc in red is the one we're talking about. But if we highlight our inscribed angle and we mark the points of the circle that we're intersecting, you can see that these two arcs are very different. So in this case, we cannot use the theorem. So we would not be able to relate the measurement of these angles at all. All right, so part 2 of the inscribed angle theorem says that when two inscribed angles intercept the same arc, then they have the same measure. So again, these pictures can get very messy, which is why it's really, really recommended to use a highlighter. So you want to find your inscribed angles, your vertex needs to be a point in the circle, right? So there might be multiple different ways that you can see this, but I'm just going to pick points A and B to be our vertices of our inscribed angles, but there are other ones in here. But if we take a look at the inscribed angle created with the vertex at A, if we highlight that angle and mark the points of the circle that we're touching, you'll see that we intercept this arc CD here. Now, if you take a different color and you highlight the inscribed angle with the vertex at B and mark those points, you'll again see that, hey, we're cutting the circle in the same exact spot. We're making the same exact arc with the sides of our angle. So what this theorem says, instead of making us do a bunch of work, we already know that the measure of this angle is going to be congruent to this angle, because again, that theorem says, hey, your inscribed angle is half your arc measure. So whatever our arc measure is here, let's say this arc measure was 60, both of these angles are going to be half of that, right? So this would be 30 and this would be 30. So this is just an extension of that theorem to save us from doing some extra work. Now, another way that you could have seen this is maybe highlighted points C and D as references. So if we highlighted the angle that C creates, or the inscribed angle with the vertex at C, we can see that we're intersecting points B and A, so we're dealing with arc AB here. And then if we take our green color and we highlight the inscribed angle with the vertex at D, again, we see that we're intersecting or intercepting the same exact portion of our circle. So again, we know that these two angles are congruent. All right, let's dive right into an example that we might see. So it says, given circle O with diameter AB, solve for the value of x in degrees and radians. So we're looking for x, so we obviously want to see, like, hey, can I solve for x without doing anything crazy? Now, if you take a look at that angle, right, we're going to have to learn how to dissect these diagrams. So For angle X right now, I see that it's an inscribed angle, and it would be really wonderful if we could just do it in one step. But the bad thing or the sad thing about this question is that we don't know anything about this arc measure here. If we knew the measure of AC, we'd be able to just take half of it, and that would be the measure of angle X, right? Like, let's say, and don't write this down, but if the measure of AC was 80 degrees, I'd be able to tell you that X was 40 degrees in a heartbeat. But we don't know that. And we don't have anything about the measure of arc AC. So we have to try to use some other knowledge. So we have a diameter here. So if we highlight that diameter, I see a central angle, right? If I see an angle going through the middle of the circle, I know we have our central angle. And we might be able to use that to help us. So if we have a diameter, we have to think about our circle getting cut in half, which means that this central angle is going to be equal to 180 degrees, right? Now, with our central angle, we can see that we're kind of cutting this into a semicircle here. We're intercepting arc AB. And let's see if we can find angle C. So if angle C, if this inscribed angle here with the vertex at C is intercepting the same arc as our diameter or as our central angle, then we'll be able to find what angle C is, right? So if we highlight angle C and we mark the points that it's intersecting on the circle, yeah, we can see that it's intercepting the same exact region, right? Which means that angle C is going to be 90 degrees. Now, we're not done yet. And we're not going to move any further into this, but what you guys should see is, always look for things that you can identify, some prior knowledge. I see that blue triangle right there. We know all angles in a triangle sum to 180, and we can kind of use that to help us find what X is, right? And then once you have it in degrees to find your radian conversion, you want to just multiply your angle by pi over 180 and simplify that, and that would be your measurement in radians. Now, another type of example that we might see is a little bit more complex. So these types of examples are going to bring back our knowledge of area of sector and arc length. So we're going to need both of those formulas. And you guys have these in your notes. So if you need to refresh yourself, you can always go back. So it says in the diagram below of circle O, the area of the shaded sector LOM is 2 pi centimeters squared. So right now, I'm making my list right away. The area of my sector is 2 pi. Then it tells us the length of NL, which is this whole entire diameter here. That is 6 centimeters. But to be honest, I feel like the radius is a more important measurement. So in my list, I'm going to write that the radius is equal to 3. And then what we're looking for is angle N. So I'm going to erase this and let's just mark the radius as 3. So our picture doesn't get too sloppy. But we're looking for the measurement of angle N here, right? And angle N, we have to be able to use our vocabulary here. That's an inscribed angle, and we know that because N, the vertex of the angle, is a point on the circle, right? So we want to see whenever we see an inscribed angle, are we able to use that theorem? So when we're given the area of a sector and the radius, we're going to be able to find the measure of this central angle right here. We're going to be able to find this. And if you take a look at the arc of the central angle, it's intercepting arc ML, but so is angle N. If you look at inscribed angle N, it's also intercepting arc ML, so we're going to be able to use that theorem, where our inscribed angle is half of our central angle. But we need to know what our central angle is first. So let's write in our formula. So we have area of a sector equals theta over 360. Remember, it's a fraction of the area of our circle, right? So we already have our area of a sector, that's 2 pi, equals theta is going to stay as a variable. We have theta over 360 pi, and then our radius squared. So right away, I see that we have pi on both sides of the equation. So I'm going to cross it out to make our lives a little bit easier so that we have less to work with. So we rewrite, we get 2 equals theta over 360 times 9. Then we can divide by 9 on both sides to help us simplify the right side a little bit. And we'll get 2 over 9 equals theta over 360. And at this point, we cross multiply. So we do 360 times 2, which gives us 720. Equals, and then we have 9 times theta. Then we divide by 9 on both sides, and we get that 80 degrees is equal to theta. Now, we always need to take a step back. Theta, remember, that represents our central angle, right? So we can go ahead and fill that in on our diagram right here. This angle is 80 degrees, but we're not looking for that. That's not our final answer. We need angle N. So I know that angle N is going to be half of our central angle here. So angle N is going to be half of 80 degrees, which is 40 degrees.